This video is part of the series on a first course in modelling, analysis and control, and focuses on an introduction to nonlinear models. Now, most real systems are nonlinear, so students need to know how to adapt their learning for linear models to that scenario. Here's an example of what we mean by nonlinear then. So imagine we've got some dynamic system here. And what we're going to do is change the inputs to that system. We could try alpha, we could try beta, we could try alpha plus beta. And then we're going to look and see what happens to the outputs. So an input alpha gives an output A, an input beta gives an output B, and an input alpha plus beta gives an output C. Now, if A plus B equals C, the system is linear. And if A plus B is not equal to C, the system is nonlinear. So that's a nice simple definition you can use to check. Here's an example then of a nonlinear function. So we're going to consider this function here, y equals x squared plus 3x plus 2. And what we're going to do is calculate this at values 1, 2 and 3. And you can see we've got y1, y2 and y3. And then you will also see on the graph that we've calculated y1 plus y2. And what do you notice? What you'll notice is that these two values, y1 plus y2 and y3, are not the same. So in other words, f of 3 is not equal to f of 1 plus f of 2. So this model is non-linear. Superposition. When a system is described by an ODE with constant coefficients, it's straightforward to show that you can solve for separate inputs and add the results, and superposition holds. So for example here with Laplace, Laplace of x plus y is the same as Laplace of x plus Laplace of y. Or if you extend this and start looking at transfer function models, you will see that if you have an input u1 plus u2, then g times u1 plus u2 is the same as gu1 plus gu2. So if you're using Laplace transforms, it's implicit that the system is linear. Here's an example with an ODE. Consider the following ODE and solve, and you'll notice I've made the right-hand side comprise of two different functions, u and f. And what we're going to do is solve independently for the impact of u and f. So for example, I first solve this equation where I've only got u, and that gives me a solution x1. I then solve with just the f, and that gives me a solution x2. And unsurprisingly, what you'll see is if I now have a right-hand side of 3u minus 0.2f, my answer is x1 plus x2. Now, I haven't proved this, but you should be able to verify or prove this just using anything you've done in a first-year maths course. And here's an example with a heating system. And what you'll notice, again, I've got two inputs, Ti and Q. So what happens if I change Q? You'll see I've gone hotter. What happens if I change the inlet temperature? And here you see I've gone colder, and you'll notice I've put a time instant here which is slightly later, about 25 seconds. So what happens if I first have a change in Q and then I have a change in T? And what you'll see is, unsurprisingly, all I'm doing is adding, that's a plus sign, those two curves to give this one. So superposition applies. So an interim summary. The response of a system denoted by y equals gu is linear, and superposition applies. Linear processes satisfy superposition, which makes analysis straightforward. So all the tools we've done in the previous videos have assumed linearity, and it means we can add the impact of different inputs and disturbance and so on, and use tools like Laplace. But here's a problem. Nonlinear processes do not satisfy superposition, and so they're more difficult to analyse and to undertake control design. And you might be thinking, well, all the tools we spent lots of effort designing, how do we use them, given that most real systems are nonlinear? And here's some example of some nonlinear systems. So turbulent flow, you often see this square root term appearing, and that will appear in tank models and the like. Anything with a polynomial relationship other than first order. A pendulum model you'll notice it has this sinusoidal term. Anyone doing chemical engineering will be quite familiar with things like activation energies and terms of that nature. And of course, there are many more examples. Linearisation, then, is the process by which we approximate a nonlinear system of equations with linearised solutions. So the key word here is approximate. It's not exactly the same, but we would like a linear model, because if we can use a linear model, it makes life a lot easier. And you'll see here a key point. It's known that in many, many industrial scenarios, a linearized model is good enough for you to do your design. Here's an example then of how you might linearize. You'll see I've drawn a curve y of x, which is clearly not a straight line, and then I've drawn a straight line approximation at a specific point. And what you'll see is as long as you stay within a certain domain, for example this domain here, the linearized approximation is good enough. So if linearization is fit for purpose, use it, because in industry the simplest good enough solution is usually best. So what do we do if a nonlinear term is present? In simple terms, we replace it by the corresponding Taylor series expansion. So you can see here the Taylor series expansion of f of x gives me f of xs, so I have to choose some point xs. I then have the derivative at xs times the deviation about xx, the second derivative at xs, followed by this quadratic term, and so on. Now, when we're doing linearization, what we do is we neglect all these higher order terms. We just take the first order term and you end up with this model here. And the key thing to note is this deviation variable term. So that deviation variable is how far am I away from the point where I did my Taylor series expansion, which will normally be a steady state. Summary procedure then for linearizing dynamic models. First thing you do, and this is really important, is you find a steady state operating point. So that means all the derivatives have to be zero. And then use some notation. It's quite common to see notation like a subscript s, the s for steady state, to denote the steady state operating point. Then define deviation variables as the distances you are from steady state. So you can see deviation variable delta y is y minus ys. How far is y away from the steady state? Approximate any nonlinear terms by their first order Taylor series computed at that operating point. So you can see the Taylor series expansion for some function y of x is y of xs, that's the operating point, plus the derivative of y evaluated at the operating point, and that should be delta y, so no, it is delta x, sorry, times the deviation in x. How far is x away from its steady state? And finally, substitute all these into your model and rewrite in terms of deviation variables, which we'll demonstrate with some examples. Here's a common example then. A tank model is given by the differential equation below. Now, if you looked at the first order models where we looked at tanks, you'll notice the main difference is that we had a linear term here, but if we want to be more realistic, that term actually depends on the square root of depth, which is what we've done here. So first thing to do, find an operating point. So we set the derivative to 0. That was part of finding the operating point. And if we do that, you end up solving this equation here. Beta root hs equals fs. So the steady state depth depends upon the steady state flow. So the two are interlinked. Next, find the derivatives of the nonlinear term. So here's the nonlinear term, beta root h. So I want to find the derivative of that term. And here it is, calculated at the steady state operating point, beta over 2 root hs. So now substitute or find the Taylor series expansion of this term. So you can see I've got beta root hs plus, there's the derivative, and there's the deviation variable. And now what I'm going to do is I'm going to take this term, or this expansion, and I'm going to plug it back into that differential equation. So you'll see what we've got here is where we had that beta root h term, I've plugged in my first order Taylor series expansion. So you can see there, all we've done is replace that nonlinear term by its first order Taylor series expansion. And then what I'm going to do is rewrite things in terms of deviation variables. So I know delta H is H minus HS, delta F is F minus Fs. So if I do that and do a bit of eliminating common terms, what you find is you've now got a differential equation which has constant coefficients. So this term, beta over 2 root hs, is simply a constant. But you'll notice everything now is written in terms of deviation variables. Another example then, mixing tank with a reaction. So here you can see we've got a mixing tank equation, and the difference from maybe a simple equation is this Ra term, which you'll notice is nonlinear. So how do we go about rewriting this as a linear model? So first, find the steady state. So what we do when we find the steady state is we set dc dt equal to 0. Now what I've done here to simplify things, you see these terms have all disappeared because I've used this value given at the top that v over f equals 20. So if I plug that in, we find the steady state is given by this expression here. Now that's not simple to solve because of the exponential, but what you can do is you can say that if Ca is small, then this term is approximately this, and so you can find a steady state, and that will be close enough in practice for your needs. Next, what do we do? Well, we define our deviation variables as normal, and then we need to do our Taylor series expansion of this nonlinear term. So you can see there's the term evaluated at the steady state, there's the derivative, and there's my deviation variable. So there's my first order Taylor series expansion. And then what I do is plug that in to my original expression. So you can see this bit here is the Taylor series expansion. So I've simply replaced this term by this term in my expression. Now what I've got to do is I want to eliminate all common terms and rewrite it in terms of deviation variables. Now you'll recognize from the previous page that the steady state terms here all cancel because we did that on the previous page. So if you do that cancellation, then you find that your model reduces to this simple form. And again, you'll notice this term in here is written in terms of the steady state value, so it's a constant. So now I have a simple differential equation with constant coefficients expressed in terms of deviation variables. Some conclusions then. This video has given a brief summary of how to linearize simple differential models containing non-linear elements. In essence, find a steady state and then replace the nonlinear terms by a first-order Taylor series valid at that steady state. The new model is expressed in terms of deviation variables relative to the steady state. Linearization is important in practice because most real systems are nonlinear, but most practical, that means easy to tune and maintain, control techniques are linear. Many real systems are operated close enough to a given operating point for the first order Taylor series to remain valid. And moreover, you'll find that deviation variables are natural in this context because they're telling you how far am I away from the operating point.